This video is running through the concept of maximum flow in the context of networks and decision mathematics for VCE Further Maths. Before we get into what maximum flow is, just a reminder, we are working here with directed graphs. And so a directed graph is any graph where an edge has an arrow to indicate the direction in which you can move along it. So usually think of that as like one-way streets or flow through a set of pipes or a network. Flow refers to the quantity that can move along that edge at any given time. So that's where we bring in the weights or the values on the edges themselves. So those weights, those numbers represent the quantity that can move along those edges. So the direction and flow are often used in combination to find out what is that maximum flow through the network. So in any one time, what quantity can move from the starting point, which is often called the source, through to the finish point, which is called the sink. So there's a number of different ways of thinking about this in a context that might make sense to you. A lot of examples use water, so the flow of water. I like to think about people or objects moving along a network. So what I mean by that is I might have 8 people who can leave the source and head to the first vertex. But the problem is there's only space for 7 people to continue along the next edge, next part of the journey. And then when I get to this second vertex, there's only 5 people who can continue all the way to the sink. So at any one time across the path along the top of this network here, there's actually only 5 people who can make it from the source to the sink at any one time. So even though I could send 8 out from the beginning, only 5 of the people will actually get to the other side. So I like to think of it in terms of that. Think about how much space is there so that each of the objects, people can get all the way from the start to the finish. So we're going to have a look at a couple of different methods to work out what is the maximum flow when you're talking about more than just one path through the graph. So we're not only considering what's happening across this top pathway, but at the same time, are people moving on the other possible pathways through the network itself? So the first method would be by inspection. It's not one that I would use. However, it is the basis for an alternative method that I'll show you in a moment, a third method that we look at. So by inspection is kind of what I was referring to just in the previous slide, where I'm thinking about in each pathway, how many people would make it all the way to the other side. So on that first pathway I've drawn there, we can see 5 people would make it to the other side. If I then look at a different pathway through the graph, I could say, well, 6 people could make it across that green pathway. So I've got an additional 6. And if I had people leave and go down the bottom edge here, they could follow through all the way, but only 2 people could make it all the way from one end to the other. So I would be saying that there would be a total of 13 people that could get from the source to the sink. So the maximum flow through this network would equal 13. So we're talking about all of the objects, people, things that can get from source to sink at one time. Now you'll notice there, I didn't necessarily use all of the edges available because sometimes they become a bit redundant. If I can't get objects to the vertex at the beginning of that edge, then I actually don't need to use it, or it's not useful to allow flow through the network. So you often will find that. So that would be by inspection. We're sort of looking at all the possible paths through and noting down how many objects, what the flow is for that particular pathway, and coming up with a total. Not so bad when it's a nice simple graph where there aren't many options, but as it becomes more complicated, this wouldn't be a recommended method. We're going to look at some other methods using this same simple graph so that then we can understand the concept to use in more complex situations. The main method that is used in further maths, and one that is stipulated within our study design, is to use the minimum cut method. So what the minimum cut method is as if I am putting in a roadblock all the way through the network. So I am going to cut off the flow so that nobody can get from the source to the sink. And so if I was to imagine a roadblock right just at the beginning. So you've left your start location, you're on the first road, and you haven't really been able to get very far at all. So what the cut does, by putting in a cut through the network and blocking off all of the flow, it allows me to do a quick check of how many objects or how much flow have I cut off. So what was moving through the network on those edges at that time. And so if I do that, I can see here I get stopped on this edge here, and that had a weight of 8. I also at the same time would have had people leave and get stopped on this edge here, and that had a weight of 6. So far there are 14 objects or people that have been stopped by my roadblock. And finally, there were 2 people that possibly were moving along that bottom edge. And so altogether, I'm saying I have stopped 16 people moving through the network by placing my roadblocks in that position. What I want to do with this cut method is be able to position my cut or the roadblocks in such a way that I am finding the minimum number of people being cut off. Because what that will equal is the maximum flow of that graph. So similar to what we were looking at in the previous by inspection, where I said if I set out along the pathway, the total number of people that can make it to the other side, so the maximum number that can make it to the other side, is actually equal to the minimum number or the weight on the path. It's the same idea. So it's a way of isolating or finding all of those minimum values. So if then I was going to say, well, I'll let everyone get almost to the end. So what happens if I put roadblocks at the end, just before the sink? So again, I'm thinking about if I can travel from the start, where I get stopped, I'm on this edge that has a weight of 5. Again, from the start, I can get all the way through to this point here. I get stopped on an edge that has a weight of 6. And also I can get all the way along and I get stopped here on an edge that has a weight of 5. So again, I have a value there of that cut of 16. So I'm stopping 16 people from getting out. So at the beginning, I was blocking off 16 people. At the end, I was also blocking off 16 people. But my aim with this method is trying to find a way of blocking the roads in the least amount possible. So I always do a start and a finish cut. So just a start and a finish to get like a baseline. So 16 is my number to beat. This is where a bit of trial and error comes into it. So I think carefully about, can I cut through some of these edges with smaller values? So what would happen if I cut through sort of the middle of the graph there? So again, I'm considering from the start. So from the start, where do I get cut off? I get cut off on an edge of 5. From the start, I get stopped here, roadblock, on the edge of 6. And again, from the start, I get stopped or cut off on the edge with a weight of 2. So in total, I have stopped 13 people. And so that is smaller than the other 2. So that's my best option so far. And so I would need to continue this process until I was happy that I couldn't find another cut in the graph that was smaller than 13. And so this is where for some of you, it might become a little bit frustrating. And so you might not like doing this method, and you might want to look at an alternative where you can find something that allows you to get a cut that you feel absolutely confident is the smallest thing that you can get. And so it can become messy quickly, this method, but it is one that is stipulated by VCAR. We have to know how to do it, in the sense that we have to know how to evaluate a cut if it is presented to us on the graph. And we also have to know how to put a cut in the correct position. And I can show you how to do that using the alternative method as well. So in this case here, just to finalise this question, we're saying we think our best cut was that one of 13. Now to our alternative method. This is a more systematic approach to the by inspection method, and it allows you, no matter how complex the graph, to feel comfortable of working your way through systematically and finding all of those possible pathways and all of the minimum weights on them. It also helps you take into account if you have already used up a particular edge, and I'll explain what I mean by that with an example later on. So before I can begin this one, it is useful to have your vertices labelled. So I'm just going to go through and label these. I'm going to leave the source and the sink as they are, because I really don't need to refer to them. It's just so I can keep a track of what's happening in the middle. So I'm going to start at the top of the graph. So I'm going to work my way from source to sink, going up and across as high as I can. So from source, I can go through A, B, and to sink. And so I'm going to note that down. I'm just going to write it here, source, A, B, to sink. And I'm going to also note down what was the smallest weight on that pathway, and that was 5. Now, what's different here to just by inspection is I'm actually going to subtract 5 from all of the weights on that path that I've just identified. So 8 minus 5, 3, 7 minus 5, 2, 5 minus 5, 0. The reason I do that is that if then there was a second possible pathway moving through some of those edges, I've accounted for the 5 that has already been taken up by that first pathway. So now, once I've done that, I look to my next possible pathway. So I might say, actually I'll leave that highlighted so we can keep a track. So maybe I can go through to C, from source to C and straight to sink. So from source, C, straight to the sink. And again, noting the smallest weight on that pathway was 6. And now subtracting 6 from both of the weights there. So the reason now that that 0 comes in handy, that subtraction, is if I was to consider another pathway through D, E, up to C and across to the sink, there actually isn't any room for any additional people to go on that pathway, because I've already allocated the 6 spots in the previous path. So even if I did do that and noted it down, so D, E, C, sink, the smallest weight on that pathway is 0. So it's going to have it's not going to add anything to the flow, and it's going to have no impact on what I've done so far. And so then finally, I could come source, D, E, and sink. So source, D, E, and then straight to the sink. And the smallest weight on that pathway is 2. So now I'm ready to identify, sorry, I should take off our 2 from everything there. So now there's no more ways to get from source to sink. I've exhausted all the possible paths. And now I'm ready to identify both my maximum flow and then also show you how you can use these values as a hint to find out where your cut should be drawn. So my maximum flow will be the total of these weights that I've noted down. So when I add up those weights, 5 plus 6 plus 2 I get a flow of 13. So that's my maximum flow. If the question asked me to draw onto my graph the cut, so let's say you decided you wanted to use this method, but the question still asked you to draw a cut onto your graph to show the maximum flow. What I'm going to do is use these zeros that I now have as weights on my edges as a guide. So I don't have to draw through all of them, but I need to draw my cut through as many of those as I can. They're my guide. And so I could actually draw my cut through this way. I could actually draw my cut through there. And if I check the capacity of that cut, so if I just get rid of my little working here, again, remember when I get stopped, I count that edge, sorry. So I've got 2. I am stopped here at the roadblock, so I cannot continue. So I'm not able to get through to vertex E and therefore travel on the edge with weight 3. So I actually don't need to count that one. Okay, that is a freebie. And we saw that up in our method here. From the source, I get stopped here on this edge of 6, so plus 6. And finally, coming across the top, I get stopped here, so I have that value of 5. And so again, the capacity of that cut is 13, which is equal to our maximum flow. There are 2 cuts that give me that same value, this same one that I drew on the previous example with the minimum cut method. So there's 2 options there. Both of them give me the maximum flow or the minimum cut of 13. So as I said, this is an alternative method that can help you if you find the cuts worrying because you don't know that you've got the final right answer, particularly in a more complex network. But it is something that you will still have to be able to identify the cut and evaluate some cuts. So we'll have a look at some examples now and have a look at different options of solving. First example here, a training program 1 has the cricket team starting from exercise station S and running to the exercise station O. So starting at S and finishing at O. For safety reasons, the cricket coach has placed a restriction on the maximum number of people who can use the tracks in the fitness park. The directed graph shows the capacity of the tracks in number of people per minute. When considering the possible flow of people through the network, how many different cuts can be made? We firstly want to determine the capacity of cut 1 shown below. So here we have cut 1 and we need to evaluate it. So no matter what method you want to use to find maximum flow, eventually you still have to be able to evaluate cuts in an exam setting. So again, we think about from the beginning, we travel until we get cut off. And so we've got a weight of 20. The second path, I get cut off and a weight of 12. The third one, I get cut off here and that weight is 20. And that is all the cuts, all the possible blocks there. So that gives us a total of 52. So that means the capacity of cut 1 equals 52. For part B of this question, we're asked then to find what is the maximum flow from S to O. So remember, we're starting at S and finishing at O in the number of people per minute. So here, using the minimum cut method, we already identified in the previous part that cut 1 was worth 52. And so that cut was close to the beginning. So I'm going to do a cut at the end, just before the finish, to get another baseline. And so there I've cut the edge of 22, 12, 12 and 10. So adding those up, I get 56. So at the moment, 52 is still the number to beat. So I'm looking for edges that have a smaller weight. So the combination of edges I'm going to cut through I want them to be as small as possible. And so this is where, as I said, it becomes a little bit trial and error. So if we think about maybe through here, I've got 20, 10, and 20. So that cut is worth 50. So at the moment, that's my number to beat. And so I'm just going to keep working my way through trying to make cuts that aren't bigger than 50. And this is where I find I get frustrated, because there's many ways I can do it. And if you don't see the best cut first up, it can be a little annoying. But some people can see it really easily and love this method. So it's just a matter of trying some different combinations and being really careful that you're adding the right values in. So this one here would be 20, and 10 is 30, and 12, 42, and 5, 47, and 10, 57. So that's definitely no good. 50, I think, is going to be our best cut from what I can see. So I'm now going to do the second method. So we're saying 50 people per minute is our answer here. So I'm now going to do the same question with the alternative method, but you can skip forward to another example if you prefer just the cut method. Okay, so here, same question, but now using the alternative method. So from the start to our finish, working my way from the top of my graph down. And so I am going to note from start through M to the finish at O, and the smallest weight there was 20. Subtract 20 from both of those edges, and now look to my next pathway. So next pathway, I can go from the start to T, U, N, and O. So start, T, U, N, O. And the smallest weight on that pathway was 10. So subtracting 10 from everything on that pathway, and now moving on to another option. So there's no point coming along T, even though there's 2 places left, because I have 0 places left on the edge between T and U. So I'm now going to come out of S to R, Q. This time I can go up to U, V, and across to the finish. So S, R, Q, U, V, and to the finish. And the smallest weight there was 5 between U and V. And so subtract 5 from each of those weights. And then try again. So this time I've still got space here, so I can go from S to R to Q. There's no point going to U because the path between U and V has been exhausted, but I could go to V and then to the finish. And now checking the crossed out weights as well. So the smallest weight there, so S, R, Q, V, and the finish. Smallest weight is 7 between V and the finish. So subtract 7. I now have 13 places left there. I have 8, 8, and 0. I've exhausted that pathway now. Next one, I still have room, so I'm going to keep going from S to R to Q. There's still room to V, and now P, and to the finish. So S, R, Q, V, down to P, and then the finish. And the smallest weight there is 5. So again, subtract 5, 5, and 5. And now finally, I have from S to R, Q, straight across to P, and to the finish. And my smallest weight available, I've got a 3. And so 5 spots left here, 0 left on that one, 7 and 2. I've exhausted all of the possible pathways through. There's no way to get from start to finish where there is any weight left. Okay, it has to use an edge that now has a 0 on it. So that tells me I've exhausted the capacity. So now I'm going to add up my values. So 20 plus 10, 30, 40, 50 altogether. So my capacity, 50 people per minute. So you can see that's the same as what we got with the cut method. But I feel far more confident with my value of 50 because it wasn't guess and check. I know that I've exhausted all the possibilities. And then finally, if I need to draw that cut in, remember we said you can look for those zeros as your guide as to where to draw those cuts. Okay, it does get a bit messy if you're using highlighter and colour. I'm kind of doing that just to show you rather than actually having to do it. And I can draw that cut through there where I get the original values 20, 10 and 20 gives me a cut of 50. This next question is to show you that regardless of which method you choose to use, you must always know how to evaluate cuts effectively. So in this question, we've got the flow of liquid through a series of pipelines in litres per minute is shown in the directed network below. The 5 cuts are labelled A to E as shown on the network. The number of these cuts with a capacity equal to the maximum flow of liquid from source to sink in litres is. So there's 2 things that you're being asked here. What is the value of each of these cuts? What is the maximum flow? And then how many of these cuts are equal to that maximum flow? So we can't just assume that these cuts, that one of them is the maximum flow. Okay, so first let's evaluate what we have, the values of these cuts. And so working, remember, always from the start, thinking about where you get stopped. So cut A would be 8 plus 15 plus 15, so 38 would be our value there. Now, I wouldn't normally draw onto the graph when I was evaluating it myself because it can get quite messy, but simply tracing with your finger would be enough. So from source to cut B, I'm getting stopped at 8 plus 15 and plus 10. So I actually can't get onto this edge here where the 5 is. There's no way for me to get from the start without already having been stopped by that roadblock of cut B. So here we have 33. Cut C. So again, from the source, from the start, working your way through, I get stopped here at 10. I can't get onto that edge of 5. I get stopped at 8. I again can't get onto the edge of 5, but I get stopped here at 15. So again, I've got 15 plus 10 plus 8, 33. Cut D. From the start, I get stopped here at 15. I can get onto this edge of 8, so always checking carefully that you can get on. However, I can't get onto this second edge of 8, so I won't count that. I also can't get onto this second edge of 5, but I am getting onto this edge of 10. So again, 10, 15 and 8, 33. Finally, cut E. So cut E, 15, I can get onto that 8. I can't get onto this edge of 5 from the start, it's not possible. Okay, I get stopped, or I end up in the sink first, but I can get onto the 10. And so again, we've got 15, 10 and 8, 33. So at the moment we have 4 cuts that are all a minimum. it is telling us that a number of these cuts are equal to the maximum flow. So we don't necessarily now have to go and check because we are confident there are multiple cuts that are equal, okay? And they would be to the 33, of which there are 4. So D would be our answer there. But if you weren't sure, you would want to check that 33 is actually the maximum flow. Example. So here, all areas of a property require constant supply of water. The following directed graph represents in capacity the litres per minute of a series of water pipes on the property connecting the source to the sink. Determine the maximum flow of water in litres per minute from the source to the sink. So from our source vertex to the sink. So we already have one cut shown here. So let's evaluate that to get a baseline, and that is at the start anyway. So 25 plus 20 plus 15, we get 60. And I would check just at the end to get another baseline. So 25 and 20, I get 45. So now 45 is the number to beat. Can I draw a cut somewhere in the graph that will give me less than 45? I can probably find a number of cuts that will give me equal to 45, but I can't see anything anywhere where I can get less than that. And so with this cut method, I may find it tricky to keep going through if I feel confident that I can't find another cut. However, you want to look for these trick edges that go sort of against the flow and think, could I cut through those? So if I was to try maybe cutting down this way, let's consider what I have there. So from the source, I get stopped here, so I've got 10. From the source, I get stopped here, so I've got 10. I get stopped, so I actually can't get to this vertex here, which means I am unable to get onto the edge, either of these two edges of 10 that are going back against the flow. So I actually don't have to count those values. But then finally, I do get stopped here, so I have 20. And so that gives me a cut with a value of 40. So that's a better number than 45. So I can now say that my max flow is equal to 40 litres per minute. So this is quite a tricky one. And with your cut method, you can get there eventually if you persist. But sometimes it's just about trying to think outside the square. Again, looking at the same example, but using the alternative method. So I could look at the cut one, but I wouldn't bother. If all I was doing was finding maximum flow using this method, I would just go straight ahead and start working it through. I've labelled my vertices apart from source and sink, so I've just labelled them there so we've got something to refer to. So working my way across the top of the graph, I'm going from source, A, C, to the sink, and my smallest weight there is 10. I'm going to subtract 10 from each of the edges and then look for my next possibility. So I could now go through source B, C, and the sink. So from source B, C, sink, and my smallest weight there again is 10. So subtracting 10, I can't go through B anymore because the link between B and C has been exhausted. So I'm now going to come down to D, across to E and to the sink. So source, D, E, sink. And looking at my smallest weight there is 20. And subtracting that from these values. And so that gives me a better check that I've used all of the possible paths. Yep. And that gives me a max flow of 40. And so now when I'm looking to draw in my cut to check that I haven't made a mistake. I'm looking to cut through those 0 edges. And so here, if I use those as a guide, I can see I get stopped here at 10. I get stopped here at 10. I can't get onto this edge for between C and E, so it doesn't count. And then I get stopped here at 20. So that gives me a maximum flow of this graph for 40. So 40 litres per minute. So as you can see, you can get the same answer, but it is a fair bit of trial and error using the cut method. And sometimes it can be tricky. So it's nice to have another process. If you're more of a process person, this alternative method can be really useful. Okay, that's it for this video. Thanks.